We are going to do some problems using properties of logarithms. So we're going to be using these properties, the product property, quotient, power, equality, and change of base, which we've already talked about in class and used a couple of times. But let's start with looking at these. So the log base b of m times n, you can break this up. We call it expanding. So we would expand this to log base b of m plus log base b of n. So remember when you learned that when you multiply like bases, you add exponents? Well, remember that logarithms are exponents. And notice when we have this multiplication, we end up adding. Okay, we're adding the exponents. See that addition sign there. Quotient, on the other hand, when we would divide like bases, we would subtract the exponents. So this is kind of this in logarithm form. So log base b of m divided by n will be log base b of m minus log base b of n. So we're taking one logarithm of a quotient of two values and separating it into, or expanding it into two different logarithms. If we had two logs that we were adding and we wanted to condense, that's when we would use this property in reverse and combine them into one logarithm. So if we have one log to two logs, one log to two logs, or 2 to 1, 2 to 1. You can actually do this with more than just two things. You can combine product and quotient properties in a single problem, which we end up doing here in problem 4. We're going to actually be doing 1, 2, 3. So here, this first expansion problem we're going to do is also 1, 2, 3, because this is 12 times x. So we're going to expand both of those. Okay, so that's going to be an exciting problem. Okay, so we're going to look at all of these two, in these first few problems. Then we're also going to look at this power property. That's going to come into play. Where's that one going to be? Maybe we're not going to look at that one here yet. Oh no, it's coming in right here. Okay, this little 3 in front. So the power property says if you have log base b of m to the nth power, this n, remember when you raise a power to a power, you multiply that raising this logarithm, this power to this power, m to the nth power, kind of, is meaning that this n can come out front here, travel to the front and become n times the logarithm. So these properties, product, quotient, and power, help us solve a lot of problems with logarithms. Okay, so that's going to be the first 4 problems. Let's work on those, and then we'll talk about these other properties and work on the rest of these problems. Okay, now, here we go. So log base 6 of 72. I'm actually going to use this, and it's just the product property. We're just going to break up 6. Break up this logarithm 72, because I know that 72 is 36 times 2, right? So I'm going to rewrite this as log base 6 of 36 times 2. All right, well, I wanted to do that because if I break this up, this becomes log base 6 of 36 plus log base 6 of 2. All right, so I know that this equals 2. The exponent on 6 that would yield 36 is 2. So this simplifies to 2 plus log base 6 of 2. Now we could put this in our calculator using our change of base property and get an estimate if we wanted to, but we're not going to. We're just going to simplify it and leave it. So that's fully simplified. And then again, we could approximate using change of base in our calculator. Okay, let's work on this expansion here. Okay, so notice too that this is a natural log. Doesn't matter what the base is. This is base e. We're just going to use this as natural log of 5. So this is going to be the natural log of 5 minus the natural log of 12x. Well, now we have a product property situation. We have 12 times x. So this is going to be the natural log of 5 minus, and in parentheses, right, natural log of 12 plus natural log of x. Now we can expand that minus sign here, and our final answer is going to be the natural log of 5 minus the natural log of 12 minus the natural log of x. And what I really want you to notice is any values that were in the numerator are positive here, and any values that were in the denominator are negative logarithms. Negative 12, right? Negative natural log 12, negative natural log of x because they're in the denominator here. Positive natural log of 5. Okay, so that's expanding. So now condense. Let's practice this going backwards. We have log base 10. This is common log. Log x minus log 9. That's going to combine to the log of, so we're going backwards. We have m minus n. So we have x minus 9, so it's going to be x over 9, like m over n. X over 9. And that's it. Now we've got a 9, we've got a positive 9, we've got a positive 3 log 12. Okay, so this one, this exponent property, we're going to use the power property here in reverse. We're going to make this n come up. So we're going to have here, this is going to be, let's rewrite this. We're not going to change anything for that first one. We're not going to change anything here. But we are going to change this one to log of 2 cubed. Okay, or 8. You can even write that as 8 next. Okay, so now let's combine these. We're adding and we're subtracting. So we're going to have a 3 in our denominator, and we're going to have 9 times 2 cubed, or 9 times 8 in the numerator. So we're going to have a single log, and it's going to be 9 times 8 over 3. And let's see if we can simplify that. We're going to have log of 72 over 3. Well, does 3 go into 72 evenly? Let's see. 3 goes into 72 times, right? 3 into 72. I know you guys are probably already doing this on your calculator, but this is my way. Minus 1, bring down the 2, 3, 24. Okay, great. So this is just going to be the log of 24. That's our fully simplified solution. Could we put that in a calculator and approximate? Yes. Are we going to? No, it's just simplified. Okay, and I'm just putting little rectangles around these answers. I would love it on your homework if you're doing that for me too. Okay, now let's talk about these other properties. The equality properties for 5, 6, and 7, and 8 here, we're going to use these equality properties. Okay, now this just kind of makes sense. B to the x equals b to the y if and only if x equals y. Well, that makes sense because b cubed must equal b cubed, right? What else could it equal? So like if you had 2 to the 3rd power, that's only going to equal 2 to the 3rd power, nothing else. So that just makes some sense. And same thing true with logarithms. Log base b of x, meaning the exponent on b that would yield x, is going to be equal to log base b of y if it's the same exponent. So so these two answers must be the same, right? The exponent on b that equals x, if it's equal to the exponent on b that equals y, then x and y must be equal. So we have this if and only if thing again. So that means like the log base 5 of 25 equals the log base 5 of, could only be 25, right? So 2 equals 2. Okay, so let's take a look at this in practice here. So we have natural log, so that's log base e, right? Natural log of 4x minus 7 equals the natural log. So the key here is that the bases have to be the same. If this was the natural log of 4x minus 7 equals the log, or the log base 2 of x plus 5, well then we couldn't solve it. But because it's the same base, we can solve. So this is true if and only if 4x minus 7 equals x plus 5. And then we have a nice little algebra problem to solve. Let's subtract x from both sides. And we get 3x minus 7 equals 5. Let's add 7 to both sides. Sorry, plus 7. And this becomes 3x is 12. Divide both sides by 3, and you get x is 4. Boop, 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 boop. Should we test it? Sure. Why not? Do we get the natural log of, when x is 4, we have 16 minus 7. That's 9. Does that equal the natural log of 4 plus 5? Yeah. And one of the reasons you want to test this is because you really want to make sure that you're not getting extraneous solutions. So we shouldn't have like negative numbers in here. These should always be positive numbers. So be careful of that. If you're doing something with an x squared that you get like 2 answers, check them. Make sure they make sense. Make sure you get real solutions. So So important there, test. Let's put a little star there, shall we? Important, okay? We only want positive values. Okay, now I'm going to move this up a little bit here for us. Okay, so solve for x. Log base 2 of 5x minus 17 equals 3. Well, this is interesting. We're not going to use any of these special properties, really. This doesn't fit any of these, really. All we're really going to do is say, well, gosh, what do we do now? Well, guess what? Most of the time, if you have a log problem and you're not sure what to do, all you have to do is change it to an exponential problem. So let's rewrite this in exponential form. We're going to say 2 cubed, 2 to the third power, equals 5x minus, not plus, minus 17. Okay, well, gosh, that's 8, right? 8 equals 5x minus 17. Add 17 to both sides. And this becomes 25 equals 5x. And so x is 5. Does that work? 5 times 5 is 25. 25 minus 17. Yeah, that's going to yield a positive number. That's going to make sense, right? 25 minus 17 is 8. 2 cubed is 8. It makes sense. Okay, great. Now, these are using this, this exponential relationship. B to the x equals b to the y, if and only if x equals y, right? And so this is e to the 2x equals e to the 3x minus 1. Well, that's true only if these exponents are equal to each other. So we set them equal and solve for x. And so we have, let's go ahead and, I guess, let's subtract 2x from both sides. I always like to keep my x values positive. So we get 0 equals 3x minus 2x is x minus 1. Well, x must be 1, right? Or you can add 1 to both sides, and you'll see that x is 1. Should we test it? Sure. E squared, this is 2, right? 2 times 1 is 2. 3 times 1 is 3. 3 minus 1, that's going to be 2 also. So this is going to be e squared, and it checks out. Good test. Okay, now this one looks a little more complicated, doesn't it? So it's not the same base. So remember, it had to be the same base. But 36 is 6 squared. So we can actually play with this a little bit. Let's let this side actually equal 6 squared to the 3x minus 5. And now we're going to use some of our exponent properties. And we're going to, when we raise a power to a power, we multiply. So we're going to let this actually equal 6 to the 2 times 3x minus 5, which is 6 to the 6x minus 10. Okay, so now our problem is actually, so on this side though, we have 6 to the 2x minus 6, right? So we have 6 to the 2x minus 6 equals 6 to the 6x minus 10. Now we have the same base here. So now we can set these exponents equal to each other. So we're going to have 2x minus 6 equals 6x minus 10. Subtract 2x from both sides. And we get negative 6 equals 4x minus 10. Add 10 to both sides. And we get 4 equals 4x, or x equals 1. Does it make sense to double check that that works? Yeah. So let's put this into the original problem. 6 to the 2 times 1, 2 times 1 minus 6. This is going to be 6 to the minus 4. Let me make a little space for us here. This is going to be 6 to the minus 4. Does that equal 36 to the 3 minus 2? Gosh, well, we could check that in a calculator, or we can do our math and try to figure it out. But I would say that these are equal. I don't know where my calculator is, or I'd do this on my calculator. But I'm going to do this the same way I did the other one. This is 6 squared to the minus 2, which is 6 to the minus 4. So those are equal. Okay, so yes, it works. Okay, so this on this one, now to be nice and clear, I'm going to rewrite that as x equals 1 and put a box around it, make it really obvious what my answer is. Okay, I know I had to cram that in there, but that's okay every once in a while. All right, that's it.